Good morning, everyone. So today we'll start module 3. So module 2, the more circle methods, I will make video and forward to you in future. Okay. And we'll start module 3. There's bending moment and shear force diagram in beams, or bending moment and shear force in beams. Okay. So the beam you have seen in buildings. So in a building, the horizontal structure is called a beam. Okay. Normally in beams, it is also a structure. Uh, if a force acting along the axis, then we call it as a bar. If a force acting perpendicular to the axis, then it is called a beam. Okay. That is the difference. It may be material, cross section, all are same. The bar, beam, okay. There may be circular bar, same as a circular beam, and a prismatic bar or rectangular, square. So that's the same cross section, beam also. But only difference is it may be any material. It is a structure is made up of any material, but force acting along the axis or parallel to the axis, then we call it as a bar. So we have seen in the first module. Okay. If the force acting perpendicular to the axis of the structure, then it is called a beam. Okay. Now here, you assume you take any like a pen. Okay. You pen, you keep it on a horizontal manner, horizontally on any two supports under the middle of the pen. Okay. If you press it, it will bend. Okay. If you apply more force, you can break. Okay. Normally the pencil or chalk piece. If you take chalk piece, normally we break into two pieces by applying a load perpendicular to the axis of the chalk piece. Okay. If you apply a load more than it can withstand, then the material will break. Okay. Normally, with sticks also we break. How you break the stick? By bending it. Clear. If you take a long stick, we hold it horizontally and will bend it, then it will break into two pieces. Okay. So there you are applying a load perpendicular to the axis of the stick. Okay, you can imagine the stick. That is easy method to assume how the beam breaks. Okay. So here again the loads is some time acting on only one point, then we call it as a point load. Then the load may be acting throughout the surface, then it may be uniform or varying. Based on the magnitude and the point on it is acting, we can classify into different types of load. So in last year, in civil you might have learned this. Okay. If it is there in the second sem for you, then because of again this online, the concept may not be clear. Okay, no issue. Okay. And whatever we learned in civil, same thing we learn here. A little bit the procedure may be different. Okay. Okay. Now you see the bending moment and shear force diagram. Here this is also graphical method. First we'll see the introduction. So basically beam where the load is acting perpendicular to the axis is called a beam. See here also definition is there. A structural member subjected to a system of forces at right angles to its axis is called a beam. Okay. Now types of beam. So here a straight and curved beam, horizontal, vertical, inclined beam, statistically determinate and statically indeterminate beam, cantilever, simply supported, fixed, overhanging and continuous. Okay. Now here in our syllabus we solve the problem on based on these conditions. Okay. we solve the problem, or we analyze the beam, which is a cantilever, then simply supported, fixed, overhanging, and continuously. So you might have learned again, if you remember, maybe in PU or in a first year. If you may remember, or you may come across this type of beams. But anyhow, we will tell again. So cantilever means it is one end is fixed, okay, other end is free. So basically, here we deal all the horizontal beams, okay. We don't analyze vertical beams or inclined beam in a MOM. We learn only horizontal beam, or only these cases we consider. Okay. Again, and the straight beams. Okay. In this module, we analyze straight beams, horizontal beams. Okay. And statically determinant. Okay. So these beams, and all these beams we consider. Cantilever, so where one end of the beam is fixed and other end is free. So normally in buildings, the window chajja, what we call, normally here in local language we call it as a chajja. If anybody, if any other name is there, you can tell to your friends. Okay. So outside, above the window, outside the building, there will be projection be made by the concrete. Okay. So that will save the by directly entering the sun rays and raindrops. Okay. Raindrops to fall inside the building. So to save that. Okay. So they will make one protection cover or some projection. So that is cantilever. So one end of the structure is fixed to the wall, other end is free. Then simply supported beam. So on any two supports, we keep one horizontal bar or beam. Okay. It is not fixed. Just we place it on the two supports, at the two end supports. Okay. So example is in a high jump, we use one horizontal stick. Okay. So that will simply place on that, because while jumping, the sportsman, if it touches, then it has to fell down easily. Or in cricket, the bails, okay, on two wickets, we keep a bail that is simply supported. It is not fixed. Okay. So when ball touches the bail, it has to fall freely or easily. Okay. So that is the example. And recently IPL got over. Okay. So you know how the bails are kept. That is simply supported. Then fixed beam. Fixed beam means at the both the end you rigidly fix. You cannot detach easily. Okay. So a beam horizontal structure. So at both ends will fix it. You may use mechanical fasteners. Abdul Salam Attar, mute yourself. I think you kept mobile somewhere and you play something. That's why it will get unmuted. Okay. So fixed beam at the both the end by using a nut and bolt, or you may rigidly fix like in a house by putting the concrete, or you may use glue. Okay, any some adhesive, or by we are fixing at the both the end. Okay. Next, overhanging beam. Overhanging beam is uh, any one end or both the end will overhang by the support. Supports will keep, we give the supports at anywhere, not at the end places, at the middle place or middle or somewhere inside the beam, we'll give the support. But ends are freely overhanged. That is overhanging beam. Next, continuous beam. If you give more than two supports, then it is called a continuous beam. Okay. For any beam or horizontal structure, you are giving a support like a 3, 4, 5, something like that. 4, 5 supports, then it is called a continuous beam. Okay. So, examples also given. A straight beam is one whose axis is along a straight line. So, example, building frame, electric pole, brake lever, screw jack, handle, etc. Okay, straight means it is not curved. Okay. And if the axis of the beam is curved, then it is called curved beam, like arches, chain hooks, crane hooks, etc. Okay. Next, horizontal, vertical, and inclined beam. You need not explain it. So, if the axis is beam is straight and horizontal, it is called a horizontal beam. So, again, building frame, beams of bridges, etc. Next, if it is a vertically, then the electric pole is called a vertical beam. Next, inclined, for example, is given ladder. Okay. Next, statically determinant. So here, algebraic sum of all the vertical forces must be equal to 0, and the horizontal forces also 0. Okay. And moments of all the forces about a point. So that is also 0. So it should be static equilibrium. Then it is called statically determinant beam. If the number of unknown reaction components exceeds the static equilibrium conditions, it is called a statically indeterminate beam. So these conditions are very rare. Even it is there in analysis, normally we ignore it. Okay. And where the process is in control. So most of all the practical things that is statically determinant. Okay. Or static things. The normally beams are static. It is not movable. Okay, it does not move. So normally all the conditions. So that is statically determinant. Now here definition as well as examples are given. So in the exam they may ask this one. Okay, types of beam and explain it. So just one sentence explanation means a definition of that, and then you will draw the sketch. So cantilever beam is fixed at one end and free at the other end is known as cantilever beam. So this is the example. So one end is fixed, other end is free. Simply supported beam. In a simply supported beam, the beam rests freely on the support at its two ends. Okay, at two ends. Okay, it is not fixed. You can easily lift the beam if it is possible. Okay, means it is a lightweight. Okay, you can easily lift it. By using crane also you can lift it. Okay, so it is not fixed. You need not to detach or something. Just hold the beam and lift it. So that is a freely supported. So as I said, the bails in cricket. Okay, fixed beam. So here both the ends are fixed. Okay, it's called or built-in walls, or you can, if it is a metallic frame, then you can use nut and bolt, or you can do the welding. Okay, so two ends are fixed. Next, overhanging beam. See here, one end of the beam is overhang, means beyond, projected beyond the support. Okay, that is called overhanging beam. So this is one end overhang. So there are the chances that both the ends it may overhang. Okay. Next, continuous beam. So here more than two supports are provided. It may be 3, 4, 5, depends on the length of the beam, and it should not buckle. Okay, or it should not bend. Okay, to avoid the bending, we give more than two supports. Then it is called a continuous beam. So normally while constructing a house, when you put the concrete, we will give number of supports there. Okay, so that is continuous beam. Next, types of load. So there are here 5 types of loads are discussed. Okay. So first one is point load or concentrated load, distributed load. So this is also important while solving a problem. So remember this. Okay. Now point load, distributed load. So and here in distributed load you can classify. Actually, this is sub classification of this. Okay. distributed load, it is uniformly distributed load and uniformly varying load. Even when uniformly varying load also distributed load. Okay. Again, uneven also there, but in our subject point of view, our syllabus point of view, will analyze based on the point load, then uniformly distributed load, and uniformly varying load, and couple. Okay. So couple are the two equilibrium forces. So because of the couple, it tends to rotate the beam. Okay. So in these cases, the beams will bend. In couple, it tends to rotate it. Okay. So here examples there, point load. Okay. So actually, in practically it is very rare cases where we can find a point load, but there are the cases are there. Okay. So at a point, as it must have some contact area. Okay. And so at a concentrated load, at any one point load is acting. Okay. So that is called point load. You are like you take a stick, you just apply a load by your finger. Okay. By you are pressing a stick only using a single finger, then it is a point load. Okay. Next, distributed load. So distributed load means along the over a surface of the beam, there is a load is distributed. Means you are keeping a book on a table. Okay. So on a table we keep a laptop, books, and many things will place. Okay. So that is a distributed load. Yeah, it is best example on a book. If you keep a books, laptop, and a pen or a pen stand, all those things. So all are very different weight is having. Okay. So laptop is having some weight. Another book may have another weight. Okay, different magnitude. Okay. So when you keep all these things on a table, on each point it undergo different magnitude load. Okay, that is called distributed load. Okay. Uniformly distributed load. So throughout the table, we are keeping same magnitude weight. Okay. If you are keeping books, all the books weighing the same weight. Okay. Same weight. Say we have some bigger, thicker books. Some 10 books we are keeping side by side on a table. So all books are weighing all books are equal weight. Okay. So when you keep on a complete table, some 10 books side by side, then it is a uniformly distributed load. Okay. And this is important to remember. For the point load, we use show the simple, the sign this one like this, pictorial representation. Okay. So this is point load. And for uniformly distributed load, here point load Newton or kilonewton is the unit. Okay. For uniformly distributed load, okay, kilonewton per meter. Okay, per meter. Okay, or Newton per meter. Okay, or Newton per millimeter also okay, centimeter also okay. But here in the book we follow the in meter. Okay, remember. So Newton per meter or kilonewton per meter. That is the unit we follow. Remember for uniformly distributed load. So per meter this much magnitude is acting. Next, uniformly varying load. Okay. So uniformly varying load. So here you can see. Suppose at left end it is 0. So at a constant rate it is increasing. Okay. So at the right end, so the W magnitude. Okay. So at a constant rate, it may be increase or decrease. Okay, you are analyzing from the right end, so it is uniformly decreasing. If you are analyzing from the left end, it is uniformly increasing. Okay, it's left to you. Here, while analyzing, you can analyze from the right also. You can analyze from the left also. Is left to you. Okay. So it's a uniformly varying load. Next, couple. Okay. So couple normally it is a load by distance. Okay, because of the couple it may rotate. Okay. And so beam may rotate. Okay. So here in this case, if the couple is acting like this, so left hand it may the beam gets lift up, and at the right hand it may go down. Okay. Suppose it is on a wall. If you are keeping a beam and you are applying a couple, so here it may get lift up. Here a wall may crack. Okay. So because of the load, the wall may fell down or beam will bend like this, inclined. Next, types of support. Okay. Hinged support, roller support, fixed support. Okay. So here actually, while solving problem, so types of support is not that much important, but in a future subjects, it is very very important. The types of load. Okay. The first one, hinged support and roller support. Here hinged and roller support. Here it may okay. Now here in mechanics of material, we are concerned only with the vertical movement of the beam. Okay. In a higher semester, you need to deal the horizontal movement also, because when you apply a load, there are the things it will move in a horizontal direction also. But here, mechanics of material, we deal only with the vertical movement. Okay. Anyhow, hinged and roller support means it will have the horizontal movement also, the displacement. Okay. So that is a translational displacement along the plane of rolling. Fixed support means we are restricting the horizontal movement, so it can only it can bend the beam. Here, this is like a simply supported because it is not fixed. We are just kept on a two supports. Okay. So when you kept on a two supports, so the beam can move horizontal direction also, or it can get lift up also. Okay. So it's like a bales, you can lift up. Okay. And so here, we are restricting all the direction, x, y, z movement. Only it may bend. Okay. Or only it can bend. Next, shear force and bending moment. This is again important definition. Okay. So shear force is the algebraic sum of the vertical forces acting to the right or left of any section considered is known as shear force. Okay. Now there is a okay. Now this is the way it is acting. Okay. Now we take a now with respect to left hand we analyze. Then the algebraic sum of all these forces to the right side. So that is called the shear force. Okay. If you are analyzing from the right hand, so algebraic sum of the forces acting on our left. Okay, that is called shear force. Okay. Again, I told you, you can analyze with respect to left hand, you can analyze with respect to right hand, or you can analyze with respect from the starting from the mid also. Okay. So if you, this is our reference pointer, like a midpoint or any plane. Okay. Any point on a beam you can consider as a your reference point. So suppose if I consider middle of the beam. So whatever the any number of magnitude loads are acting on our right side, the total algebraic sum of those forces is a shear force. Again, any number of loads acting on our towards left side or left of the section. So the complete algebraic sum of all those loads are shear force. Okay. Okay, this is shear force. Normally we write in short form SF. Okay, that is shear force, and we show it the variation of the bending or the effect of this shear force along the beam is called a shear force diagram. Okay, so that is denoted by SFD. Next, bending moment. So the algebraic sum of the moments of all the forces acting to the right or left of any section is known as bending moment. Okay. Now, here because of this load, it will bend like this. Okay. So that is a bending moment. That is load into distance. So if you apply load, now we are analyzing with respect to left hand. If you apply load here a little bit far away from the this fixed point, so we will get more deflection. Okay, more, it will bend more. Again, effort is required is less. You learned in a primary. Okay, if you take any lever or if a spanner while locking and unlocking the bolt or tightening or loosening the bolt, if the spanner is longer, then you need not to put more effort. Okay, by less effort you can easily loosen or tighten the bolt. If the spanner is very small, we need to put more effort to loosening or tightening. Okay. Same normally in the schools, they will give the example of the door, opening and closing of the door. Okay. So door is fixed at one end, one side. Clear? Uh, if you apply a force to open a door, if you want to open a door, if you normally where we apply a force at the other end. Okay. Because there you can easily open. Suppose at the fixed end, if you are applying a force or if you push it, you cannot open the door easily, right? So similarly here, so when you apply a load here, so it will bend. Because of this effect, it may bend the magnitude will be different. So the sum of all bending moment is called bending moment diagram. Okay. Bending moment. Now sign convention. This is very very important. Remember, if you note down, then it's good. Okay. Sign convention for the shear force. Okay. So here it is little bit difficult to understand. Okay, you note down this sign convention. It is easy to understand here while solving problem also. Note down this sign convention for shear force. Now this is a beam. You can select the cross section anywhere or a reference point. Okay. From your reference point, if any force is acting downward to the right of your reference point, then it is called a positive shear force. Okay. And from your reference point, any forces are acting to your left side. If it is a upward forces, then it is a positive. Okay. On a beam, you can select any reference point. Okay. Or you can select any section. If the force is acting downward on right side of the section, then we consider it as a positive shear force. On the left side of the section, if the forces are upward, then we consider as a positive shear force. You draw the sketch. If you want, you can write on your own word. So similarly, on a beam, whichever point you consider as a section or a reference point, on left side, if the forces are downward, then it is called a negative shear force. And on right side, if the forces acting upward, then we consider as a negative shear. opposite to this. Okay, hope you copied this. Next, bending moment. Okay, so here it is a beam. Okay, now if it beam if it bends like this, or smiley, okay, or sagging, so that is positive bending moment. If it bends like this, hogging, okay, so then it is called a negative bending moment, or a sad space. Sorry, sad face. Okay, this is smiley. This is sad face. So here, technically speaking, the bending moment to the section on right side is the couple acting counterclockwise direction, then it is positive. On left of the section, if the couple is acting clockwise direction, then it is called positive bending. Here it is reverse. To the right clockwise is negative, and to the left counterclockwise is negative. So in beam, wherever the section you have considered, to the right side, counterclockwise couple is positive, clockwise couple is negative. To the left of the section, clockwise is positive, counterclockwise is negative. Again, this is also important. Note down this. See here, now it is a cantilever beam. You are applying a load on right end of the cantilever beam. So because of that load, it will bend like this. So this is hogging, and couple will be like this, clockwise. So that is negative bending moment. Suppose here force is applying upward. So here this fixed point I will take it as a reference. Okay, force is acting upward. Okay, so shear force is negative, bending moment is positive, because the cantilever beam will bend like this, like a moon, half moon. Okay, the beam will bend like this. So the couple is counterclockwise. Okay, couple is counterclockwise. This is the reference point. On the right of the reference point, couple is acting counterclockwise direction. Or a beam will bend like this, like smiley, or sagging movement. So that is positive. If you are considering only shear force, if now this is our reference point, right, this is the right side of the reference. Okay. So upward force, if the force is, you are giving here one support, so that is actually negative shear force. Okay. So there is no support. Here you are applying like on a board, like I don't know what is the name. Normally in Olympic, the swimmers they will jump from the one springboard or something. Okay, into the swimming pool. So they will stand here. So when they stand here, it will bend like this. So shear force, that is load is acting downward. Okay, so that is positive shear force. Okay, sign conventions are clear, I hope. Okay, now we'll solve means a small derivation. Now, sign convention over. Now, one this is actually important. Many times to make, if they want to make question paper easy, they ask this derivation. It's very simple derivation. Okay. Now here the derivation is a relationship between load, shear force and bending moment. Okay. Now this is the sketch. So here figure shows a beam carrying uniformly distributed load of W per unit length. Okay, here this symbol is for UDL. Okay, UDL, uniformly distributed load. Okay, and it is simply supported beam. So this is the arrow mark here. Okay, here you can see. So this arrow mark. Okay. So that is both ends. There is a support for this beam. Okay, for beam there must be support. Okay, these are the two supports. Now this is simply supported beam. Okay. Okay. W per there's a UDL means W per unit length or W per meter which is. So consider a small portion of the beam PQ. Now this is the total length of the beam L. Okay. AB. We'll consider only small elemental. Okay. Say P and Q, small elemental length dx. Okay. Dx at a distance x from the left hand support. Okay. So from this is the left hand support. So at a distance of x, we consider small elemental length dx the portion of the beam. The load acting on the portion BQ is equal to W into dx. Okay. So W is the magnitude, dx is the length, because UDL we measure unit per W per unit length. W per unit length, Newton per meter. Okay. So Newton is magnitude per meter, that is per unit length. So here, here total load is W dx. Suppose, for example, 1 kg per meter load you are applying. Okay. For 2 meter, the total magnitude is 2 kg. Okay. So here the calculation is the, load if it is a UDL I am telling you. Okay. 1 kg per meter means for 2 kg, for 2 meter it is 2 kg, for 3 meter it is 3 kg. So load into distance, the total magnitude. Okay. So here same W into dx, load into distance. This is the total magnitude of the UDL. Okay. Let shear force at P, F is equal to shear force at P. Now here one force is acting. So here arrow is showing is downward. So this is downward shear force. Another shear force at a distance of dx or point Q, and F plus df, that is the magnitude of this shear force. Next bending moment at P, M. So this is here one bending moment is acting, M. Okay, so now if P is the cross section, to the left there is one couple is acting, M. Another couple is acting at Q. Okay, bending moment at Q. Okay. Now the small portion of PQ of the beam is in equilibrium. Therefore, the forces and moments must obey the law of equilibrium. Okay. Now, the resolving the forces vertically on the elemental portion. Okay. F plus W dx equal to F plus df. There are, so this derivation I have also solved. Okay. Okay. Here the student have done here. Okay. So here the downward forces and upward forces should be equal for equilibrium conditions. So here F force is acting downward, W dx also acting downward, because uniformly distributed load it is on the above beam. So the effect is downward. And this is upward force. Okay, F plus df is the upward force. So downward forces must be equal to upward forces. Same. F is the downward force. W into dx is the downward force. So that must be equal to upward force. So this is the upward force, F plus df. Okay. So when it is equal, now when you simplify this, so F and F gets cancelled. Okay. So only W is equal to delta F by delta X. Okay. So the rate of change of shear force is equal to the intensity of the load. Shear. So over a distance, the rate of change of load, shear force, is equal to the magnitude or intensity of the load. So W equal to del F by dx. Next, equating the moment of forces at Q. Now this is the relationship between weight and the rate of shear force. Next, equating the moment of forces at Q. Okay, now with respect to Q. Okay. Now here this couple is acting now with respect to this on left side. So this is the effect of this moment is sagging. Okay, sagging. So that is positive bending moment. And there is a force acting. So force into dx. Moment is or couple is load into this side. So this is this effect the beam will bend like this downward. So that is hogging. So hogging is a negative bending moment. So that is minus F dx. Then uniformly distributed load. So normally the uniformly distributed load for bending, what we consider, it is acting at a middle portion of the section or at the CG and as a point load that we assume, okay, for analysis purpose for bending moment. So that is W into dx, this is the load, and del x by 2, this is the middle point of the section or CG of the section. Okay. So load into center of gravity of the section. So normally this one, so at the middle point, CG for this one. So del x by 2. So this is that moment, load into distance. Next, this side, only 5 minutes is there. So Jishnu, you take a screenshot of the participants. Okay. Okay. So here, so this is on left side and right side only one couple is acting there. So that is shown here, m plus delta m. Okay. Then you simplify this. So here m and m gets cancelled. The remaining is, so this side minus w into delta x square, so here multiplied by 2 minus x into delta x equal to delta m. Okay. So this f into delta x is very small and the delta x square is very, we ignore it. Okay. So remaining is now this Okay, sorry, there a little printing mistake. Now same derivation here from here. So minus w into delta x square by 2 is very small. Delta x square is very small. So we ignore this. The remaining is minus w minus f into delta x equal to delta m. Here m and m gets cancelled. So here minus f is equal to delta m by delta x. Now this is the rate of change of bending moment is equal to the shear force at the section. Okay. So this is the derivation. So one is minus f equal to delta m by delta x. That is the rate of change of bending moment is equal to the shear force at that section. So another one, the rate of change of shear force is equal to the intensity of the load. Okay, okay, this is a small derivation. We stop it here. So other materials this I will post it in Google Classroom, and module 2 those more circle diagram I will make video and post it. Okay, stop it here.